Welcome back to G Fun Facts Online. Today we are going to talk about what is arguably the most significant shift in the history of artificial intelligence, a shift that has effectively closed the chapter on the last 10 years of development. For the better part of a decade, the face of AI was a chatbot. From the early days of GPT-3 all the way to the ubiquitous assistants we saw everywhere in 2024, artificial intelligence was defined by its ability to process language. It was a librarian, a poet, and a coder. It was a master of the symbolic world of text. But there was always a fundamental flaw. It was, essentially, a disembodied brain in a jar. It knew the word apple. It could write a beautiful sonnet about an apple. But if you threw an apple at it, it would not know to duck. It had no concept of gravity, no concept of velocity, and no understanding of the messy, unyielding rules of physical reality. That era effectively ended this year, in 2025. As we close out this year, the center of gravity in AI research has shifted violently. We have moved from large language models, or LLMs, to what are now called Generative World Models, or GWMs. We are no longer just teaching machines to speak. We are teaching them to simulate. With the release of Sora 2 in September, followed closely by DeepMind's Genie 3 and the public debut of World Labs Marble, we have cemented a new paradigm. These are AI systems that possess an internal, physics-compliant representation of the world. These aren't just video generators. They are neural engines that maintain a coherent, persistent, and interactive state of reality. They can predict how a glass shatters before it hits the floor, not because they have read a physics textbook, but because they have watched millions of glasses break and internalized the causal dynamics of the event. Today, we are going to explore how AI learned to model the physical world, and why this development is the true bridge to artificial general intelligence. To really understand world models, we first have to unlearn the intuition we built up during the era of large language models. An LLM works on statistical correlation between words. It predicts the next word in a sentence. If you ask a text model what happens if I drop a ball, it retrieves a linguistic pattern that says, it falls. A generative world model, however, simulates the process of falling. This concept is rooted in the work of researchers like David Ha and Jürgen Schmidhuber back in 2018, and it has been championed famously by Yann LeCun. The idea is that for an intelligence to be autonomous, it must have an internal simulator. It needs to run a mental movie of possible futures to plan its actions. As of late 2025, these models operate on three fundamental principles. First is spatial intelligence. This is the understanding of 3D geometry and object permanence. It is the ability to know that a car still exists even when it drives behind a building and is no longer visible. Second is temporal consistency. This ensures that time flows linearly and causally. For example, a broken egg cannot unbreak. And third is physical dynamics. This is the ability to simulate forces like gravity, inertia, friction, and collision, without having these equations hard-coded by a programmer. Dr. Elena Vance, a lead researcher at World Labs, describes it perfectly. She calls it a dream engine. The AI hallucinates a future, but that hallucination is constrained by the rigid laws of physics it has learned from observing reality. It is a disciplined dream. The acceleration of this technology in the last 12 months has been staggering. We have seen three distinct approaches emerge that define the competitive landscape of 2025. Let's start with OpenAI's Sora 2. When the original Sora was released in 2024, it was a wow moment for video generation. But Sora 2, released this past September, proved to be a physics moment. Unlike its predecessor, which often morphed objects or confused the background with the foreground, Sora 2 demonstrates Newtonian reliability. In demonstrations, users have shown the model complex scenarios, like a stack of Jenga blocks being nudged. The model generates a video where the blocks tumble with frighteningly realistic, rigid body physics. OpenAI claims the model isn't calculating physics using math equations. Instead, it has intuited physics from watching petabytes of video data. It is a pixels-to-physics engine, translating visual noise into coherent world states. While OpenAI focused on video, Google DeepMind focused on interaction. Their breakthrough is Genie 3. This builds on the game N-Gen paper from late 2024, which famously simulated the classic game Doom entirely using a neural network at 20 frames per second. Genie 3 takes this concept to the general world. It allows users to take a single image of a real-world street and effectively play it. You can control a camera or a character and navigate the space. The AI generates the new perspective on the fly, predicting what is around the corner or behind a car. It is effectively a neural game engine, rendering reality in real time without a single polygon or texture map, generated entirely from latent space predictions. Then we have World Labs, founded by AI pioneer Fei-Fei Li. Their model, called Marble, released in November 2025, takes a more scientifically rigorous approach. It eschews the dreamy quality of video generators for pure spatial intelligence. Marble creates persistent 3D worlds from prompts. Unlike a video that plays and vanishes, a world generated by Marble has a permanent state. If you open a door in a Marble simulation and walk away, the door stays open when you return. This concept of object permanence is the holy grail for robotics, as it proves the model has a robust internal memory of the environment's topology. Finally, we have to look at Meta's approach with VJEPA 2.0, or Joint Embedding Predictive Architecture. This follows Yann LeCun's philosophy, which is, do not predict every pixel, predict the concept. JEPA doesn't try to generate a photorealistic video of a car crash. Instead, it predicts the outcome in an abstract representation. It effectively says, the car will be damaged and its velocity will be 0. This approach is far more computationally efficient and is currently the leading architecture for training autonomous agents that need to make split-second decisions without rendering a high-definition movie in their heads. Now you might be wondering, how do they actually simulate physics? This is the most heated debate in AI today. It is the stochastic parrot argument, but applied to Newton's laws. Proponents of the intuitive physics hypothesis argue that if you train a model on enough data, such as dropping balls, flowing water, and collapsing buildings, the most efficient way for the neural network to compress that data is to discover the laws of physics. For example, to predict the next frame of a bouncing ball, the model effectively learns a vector representation that behaves exactly like the formula for gravity, F equals ma. It hasn't been taught the math, but its internal weights approximate the function perfectly. Newer architectures, particularly in Sora 2 and Genie 3, use a technique called latent dynamics modeling. This works in 3 steps. First, compression. The visual world is compressed into a latent space, which is a simplified mathematical representation. Second, transition. A dynamics model predicts how this state changes over time, for example applying a velocity vector to the ball vector. And third, decoding. The new state is decoded back into pixels for us to see. This is strikingly similar to how video game engines work, calculating logic in code and rendering it to pixels, except here, the code is a black box of billions of parameters learned from observation. So why does this matter? If you think this is just about making better Hollywood movies or video games, you are missing the bigger picture. Generative world models are the missing link for embodied AI. Let's look at robotics. Robots are notoriously hard to train because reality is slow and expensive. If a robot needs 10,000 tries to learn to pour coffee, you cannot do that in a real kitchen without making a massive mess. With models like Genie 3, researchers are now training robots inside neural dreams. The robot's brain is plugged into the world model, which feeds it synthetic visual inputs. The robot moves its arm, and the world model predicts how the cup moves. This Sim2 real transfer has solved the data bottleneck for robotics. In 2025, we are seeing the first wave of humanoid robots, like the new Figaro 3, that learn to walk entirely inside a generative simulation. It is also revolutionizing autonomous driving. Self-driving cars have stalled because they struggle with edge cases, those rare, weird events, like a horse running on a highway. You cannot collect enough data on these because they rarely happen. World models allow companies to generate these scenarios. An autonomous driving system can now be tested against millions of hours of AI-hallucinated nightmare scenarios, like blizzards, jaywalking pedestrians, or debris slides, that follow realistic physics, ensuring the car knows how to react before it ever hits the road. Even in science, these models are becoming virtual labs. In material science, models like Marble are being used to simulate the stress tests of new alloys. Instead of physically building a bridge to see where it breaks, the world model, fine-tuned on structural engineering data, can simulate the collapse with high fidelity, allowing engineers to iterate at the speed of silicon. Of course, the rise of world models forces us to confront uncomfortable philosophical questions. If an AI can simulate a world with consistent physics, time, and causality, at what point does that simulation become a reality? When Game Engine simulates Doom, the monsters inside react, fight, and die. They are agents in a consistent reality, generated by the neural network. Current leading cognitive scientists suggest that human consciousness is effectively a world model running on the hardware of the brain. We don't perceive reality directly. We perceive our brain's prediction of reality. If AI systems are now running the same architecture, predicting sensory inputs based on an internal model, are we witnessing the first sparks of machine consciousness? Most researchers, including LeCun, say no. They argue that these models are still zombies. They are simulations without a self. They predict the what, but they have no drive, no emotion, and no self-experiencing the simulation. They are simply excellent predictors of the next video frame. However, the power to simulate reality comes with profound risks. Even the best 2025 models still glitch. This is called the mirage effect. A generated video might show a car merging into another car without crashing, or a person walking through a wall. If we rely on these models to train safety-critical robots, these glitches could lead to catastrophic failures in the real world. Then there is the issue of deep fakes on steroids. Sora 2 allows for the creation of video evidence that is physically consistent. Shadows fall correctly. Reflections in eyes are accurate. The line between recorded reality and generated reality has dissolved completely. And we cannot ignore the compute costs. Running a high-fidelity world model requires immense energy. The carbon footprint of dreaming a complex simulation for 24 hours rivals that of a small neighborhood. As we look toward 2026, the next step is obvious: convergence. We currently have LLMs, which reason, and world models, which simulate. The holy grail is to merge them. Imagine an AI that can reason about a problem, such as noticing a leak that needs fixing, and then run a mental simulation of fixing it using a world model to see if the plan works, before finally executing it with a robotic body. This is the path to artificial general intelligence. A GBI will not be a chatbot that knows all the answers. It will be an agent that understands the physical consequences of its words and actions. Generative world models have given AI a body and a world to live in. Now, we just have to wait and see what it decides to build in there. Thanks for listening to G Fun Facts Online.